This is a video that I'm making to support a college algebra course that I'm teaching. And specifically, we're going to go through the Unit 3 review homework, just to make sure if you have any issues understanding some of the content from the lesson, since the Unit 3 time frame was very, very short. It was about 2 weeks for the entire unit. It's different than we're used to. We normally have more time on these assignments. So I'm going to go through the homework so you can kind of see how each of these problems gets solved. And then, of course, your numbers are going to be different and your order may be different. And then, of course, when you take your test, it will usually mirror the review very closely. So the first question we have is, which of the following graphs represents best y equals to square root of x, and what is its domain? So you're supposed to memorize these. They were presented in chapter 2.6, section 6 of the Unit 3 lessons. And if you remember, we have this sort of U shape is a parabola. It is attached to x squared, the squaring function. This kind of funny looking swoop shape, S looking shape here. This is a cubic or some higher degree, odd degreed polynomial. And so then we have one that we haven't actually talked about in class yet. And the last thing that we have is a function that takes the square root. And so pretty quickly we can look at the square root and identify that D is the graph of the parent function. And then, of course, it asks you to state the domain for that as well. So keep in mind that the square root function, it begins at 0 and it continues forever in the infinity direction, but there's nothing over here on the left-hand side unless there is a shift in the graph one direction or the other. Question 2, we have a graph about which functions are increasing over their entire domains. And increasing just means that if I look at the continuous portion of the line, in other words, the where my pen would draw if I was trying to draw this shape right now, if the path that my pen takes is generally in the upward sort of direction, then we say that this is increasing. And a special note about that is that what we're kind of secretly talking about here is the slope. So that omits graphs like C, because even though this step function, this is what this thing is called, does have a general upward trend, you'll notice that at each continuous part of the line, the slope is actually 0. In other words, these little steps, they're straight horizontal. They never actually have positive slope. So we don't say that this thing is increasing for that reason. So graph A, we notice that the slope is generally positive the entire time on here. And so that means that graph A is definitely increasing. Okay, graph B, we have a portion of this where it is increasing, but I also have a portion of this parabola where it's decreasing. Now the other thing that is kind of a funny thing about the way that Pearson worded this is if you notice it says which graphs of functions increase, and graph B actually is not a function because it does not pass our vertical line test. So you know that means if I drop a vertical line, it crosses in 2 different places, and I've tried to illustrate that with this red pen that is running out of ink. So that means that the only other option is to check graph D, and you notice that in general the slope of this line is pointing up over its entire domain. So the 2 functions that we want are A and D, which are increasing over their entire domain. Part 3, you are asked about a piecewise function, and these are relatively new to most of us. Algebra 2 during the years of COVID didn't stress these maybe as heavily as we would like, so this is new to us in college algebra. And the tricky thing to this is just to be really, really comfortable with this notion of function notation, where f simply denotes what rule we're plugging into, and the number inside denotes the number that we're going to send through that rule. So we need to look at what each of these is asking us for. It says let's send -4 through f. Let's send -1 through f, 0 through f, 2 through f, 5 through f, etc. Well, f is split into two parts, 2x and x minus 1. So which part do we use? Well, we want to compare the number that we're supposed to plug in to this support over here on the right-hand side. And the support is basically telling you where to plug that number in. If x is less than -1, and in class I've always referred to this as if x is to the left of -1 on a number line, you know, we draw our number line, and here's -1, where would we put -4? Well, -4 is like right here. So on the left-hand side of -1, we plug in -4 to 2x. On the right-hand side of -1, we plug it into x minus 1. So -4 is on the left. I'm going to stick that into 2x. 2 times -4 will ultimately equal -8. Then it says, what is f of -1? So what is f of -1? -1, if you look very, very carefully at this, you got this little line under the support there. That means that when x is less than or equal to -1, in other words, to the left of and including -1, we stick it into the equation 2x. Expression 2x, excuse me. So 2 times -1 will give us -2 as our output value. f of 0, compare where 0 is to -1. 0 is over here on the right, and so that squarely fits into the x minus 1 portion of our rule, f of x. 0 minus 1 gives us -1. Now the next two, I'm not gonna go through the comparison steps. I mean, of course, you can see that they're 2 and 5. They're even further to the right. So 2 minus 1 will give us 1, and 5 minus 1 will give us 4. On question number 4, we are supposed to describe the way that each graph has been related back to this simple thing. And it's worth noting that we saw this in the notes and we saw this in the lectures, and I've referred to it many, many times, that this thing is called the parent. And it's basically just the easiest version of that rule that you could possibly write. So if I want to write a squaring function, or in other words a quadratic, the easiest version of that I can do is just x squared. And then every other quadratic can be built out of that function. In other words, it's like every other quadratic is a child of the parent. So if you have a TI calculator, one thing we can do, since we have the technology, is simply plot the parent and then plot what you were given. And so the first line it draws is the parent, and the second line it draws is the child. So we just say, okay, how does the child compare? Well, it's the exact same. This graph on the right is exactly the same as this graph on the left, with the exception that everything has been bumped over to the right by 3 units. And we can very, very clearly see that that's translation 3 units to the right. Now again, we are supposed to compare a graph of f to x squared. So I have 7x squared. How does that compare to x squared? And again, with technology, we can type the parent first and then the child, and we can graph it. I mean, literally just compare the graph here. So notice that the first line, that's the parent. We know what that looks like. This one's been like stretched out somehow. So this is kind of where the limitations of the calculator start kicking in, where you have to actually know some things. So first of all, this was posted in the Google Classroom, and I'm sure that you can go back and find this in your notes somewhere. But we know that if we add or subtract a constant on the inside of the parentheses, just like we did in question number 4, then this translates our graph left and right. And it should be noted that the left and right movement is actually the opposite of what you think it is, because that -3 in number 4 moved the graph to the right instead of to the left. It's kind of the opposite of what you think it should do. Well, this rule that we need to know is what happens when you multiply something on the outside of f of x. Well, keep in mind that in like old-fashioned Algebra 1, we said that what a function is it takes some input like x, it passes it through f, and it spits out a y. And we used to write these as ordered pairs, x comma y. So then you got to Algebra 2, and we started saying, well, for all intents and purposes, f of x is actually equal to y. So what if you multiply all of the y values by a certain number? Well, then notice that the place that those values happens in the x direction is still the same thing. For example, if I take 1, 2, and I multiply it by 7, well, then the new pair is 1, 14. I should specify I'm multiplying the y coordinate by 7. So nothing happened in the xy direction, or nothing happened in the x direction, and you can clearly see that on the graph, where nothing happens in the x direction. But all of these y values kind of get picked up by a certain amount, which we call a vertical stretch. So then we have to state the factor. The factor is 7. Now we know that numbers multiplied on the outside of the parentheses change your function in a vertical sort of direction. So if you have a negative multiplied to the outside, it has the effect, our example, it takes an x, passes it through f, sends it to a y. Suppose that 1 was sent to 2, that's the ordered pair 1, 2. And remember that f of x, for all intents and purposes, is y, the y coordinate there. So if I just make the y coordinate negative, that has the effect of reflecting this thing across the x-axis. So we know this is reflected across the x-axis. And the other thing we know is that with the plus or minus on the inside, that tells us about a translation, some direction, left or right. So this is a translation of 9 units to the left, because remember, it's kind of the opposite of what you think it should be, and a reflection across the x-axis. Answer choice should be B. They might ask you to pick from a graph. And most of the time they don't have a scale factor, because that's kind of hard to see on these little tiny graphs like this. So you want to first find a point that should be easy. Normally the vertex here is at 0, 0. So you say, okay, where does this thing get sent? Did it get sent in the left and right direction? And the answer is no. So if you recall, any f of x where you have something added or subtracted on the inside of the parentheses, here, here, and here, that's going to send it to the left and the right. And so these have, all three of these, B, C, and D, they've been moved to the left or the right, some direction. We don't even really care where they've been moved, but we know that it's not supposed to because of our graph. So that brings up a good point. What happens when you add or subtract a number on the outside? When you add or subtract a number on the outside, it just moves the graph in an up or down sort of fashion. And you can kind of think about this. This is like taking the y coordinate and adding a certain amount. So if the original point is 0, 0 on the parent, and then I just add 4 to the outside, well then that sends this ordered pair to 0, 4. It moves the dot up, but not left or right. So if I have a minus 5 on the outside, that should send the dot down 5. Okay, you're asked to graph the function provided here. And I am noticing this has cut off some of my answer choices. So anyway, we'll just draw it. Oops. Okay, so we have our graph. Maybe I can do a little bit better here. Do it with a straight edge. We have our graph, and I can go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the same in the y direction. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, there's my graph. Now I know that the x squared function is supposed to be centered at 0, 0, 1, 1, 2, 4, negative 2, and 4, and it makes this parabola shape like that. So looking at the rule that we're given here, a couple of things have happened. Let's combine everything that we know so far. The plus 4 on the outside is going to take each y coordinate and it's going to move it up that amount. So every single one of these dots kind of just goes 1, 2, 3, 4, and like that's the new place for the vertex. And the minus 5 part on the inside is going to have the opposite effect. This is going to move it to the left 5. So it's 1, 2, 3, 4, 5. This is kind of the new point. So if this is the vertex, I'm going to call it A. Then this is the first image of it, and this is the second image of it. It's like one move, two moves. And then the last thing that we have is this little negative on the side, which we know on the outside, that reflects it from top to bottom. So if the vertex was here, normally it kind of opens in this way direction, but it's going to reflect so that it opens like this. And then, of course, we pick the graph and the answer choices that matches. It appears that B is pretty close to the correct graph, but without being able to zoom in on that, I'm not going to stake very much on that. Now, I'm not going to go through this problem in very great detail. But this problem is just seeing how well you can follow those rules that we discussed in the previous problems up until now. So the only rule we have not discussed is a negative on the inside here. And a negative on the inside of the parentheses is like flipping the x coordinate. So you know that if I have an x and it passes through some function, I'll call it g because this one's called g. It's going to map it onto a y coordinate. So let's say 1, 2 is an ordered pair. That means that 1 gets passed through g and spits out 2. That's the ordered pair 1, 2. And the negative x part is kind of like saying, well, let's just make the x coordinate negative. So instead of being on the right side of the graph at positive 2, it's now on the left side of the graph at positive 2. So this kind of rule here, f of negative x, is going to correspond to a reflection across the y-axis. So you'll have to kind of pick your favorite point and follow where it goes, and I think we've done enough practice in class for you to know how to do that, but notice that the graph on part A is simply reflected across the y. And then you'll have to pick the description for each. Okay, so maybe they don't actually tell you what the rule is, although you should be able to pretty easily identify that this thing is, let's try this here, see if I can get it to focus a little bit better. Okay, so you may be able to recognize that this is a cubed graph. This is like x to the third power, but let's say you don't, and it still says graph f of x minus 3. Well, again, it's cut off some of my answer choices, but notice that all that should happen when the number is being added or subtracted on the inside, that's a movement in the left or the right direction. And it kind of has opposite effect of what you think. The negative 3 should move us to the right 3 units. So you simply take this graph, whatever it is, and you move it to the right 1, 2, 3 units, and then you just graph kind of the same thing. And of course, I've done a very bad job of drawing it, but you kind of catch the meaning. You should be able to pick it out. Okay. This portion in the test review is where we've moved on to 2.8. And this is kind of all of the stuff that I was noticing people were having the most trouble with. So, little tricky thing that you can do here is when you're doing compositions of functions, and what I mean by compositions is that you have some kind of rule that says that you need to take f, which is a function, and subtract g, or like maybe you need to take f and multiply g, or like take f and subtract g, g subtract f, g plus f, any of those things. Then what you need to do is take each of the rules that you've been given and kind of write them out one on top of the other so that we can create addition and subtraction problems very easily if we need to. The multiplication, unfortunately, I don't have a really wonderful trick for remembering this, but it's easy enough to understand. If you want to take f times g, maybe you like draw your area model and we do it that way. So on 12, we're going to first write 2x squared, because this is the rule for f, and then g underneath it. Now notice that g does not have an x squared term, so I'm going to skip a space. Now g does have an x term, so I'm going to write that in. But notice that f does not have an x term, so I'm going to skip a space, but x does have a constant, and so does g, plus 1 and plus 6. So I kind of wrote it in this like weird spaced out sort of fashion. But this has the effect of dividing this into 3 separate sections for you to figure out. So let's do f minus g. We move in each section, and we're going to take the term on top, the f term, and subtract the term on bottom. 2x squared minus nothing is just 2x squared. Now, if there's a blank on top, we kind of have to include a 0. And 0 minus negative 2x is like adding 2x. So then we have 1 minus 6, which should give us negative 5. And this problem asks us to plug in a number, negative 4. So I'm going to do that in each of these spaces. At this point, what I want you to take special note of is that especially when I'm plugging in a negative, that I'm always putting a parentheses around this, because, let me just show you. If you don't do this in your calculator, the calculator's kind of dumb, it doesn't understand what's going on. It's going to attempt to turn that into a negative number. Although we know if you take two negatives, negative 4 times negative 4, we should get positive 16. So the way that you fix that is you put a parentheses around it in the calculator. So when I type this whole kind of number sentence thing out, I'm going to get, let me put it where we can see both the number sentence and my calculator screen, 2 times negative 4 squared plus 2 times negative 4 minus 5. And we should see that this is 19. An alternative, if you're given a number, remember we can just handle the parts separately. If I plug 4 into f of x on number 13, I have 4 minus 5, which is negative 1. That's the first part. If I plug 4 into this second part, I have 4 squared, which is 16. Then I have 5 times 16, which is a lot. But then I have minus 4 times 16, so 5 times 16 minus 4 times 16 is just 1 times 16, so that's 16. And then 16 minus 4 will give us 12. And this f times g business tells us to multiply the two results together. So this is result number 1, this is result number 2. If I multiply them, you will see that I get d, negative 12. And it's kind of up to you how you'd like to do that. There'll be a follow-up video before Monday that talks about the domain problems and the actual function composition, g of f of x, f of g of x. But this should get everybody going in the meantime.